Hi, everyone. My name is Yuan Yao, and today I'll be presenting our work called Cosmic. This project is driven by a simple question: can we run real-time control loops for 3D printing entirely in the cloud using low-cost serverless platforms and still meet the strict time constraints? In case you're not aware or missed Daniel or Shusha's talk, let me tell you more context about serverless computing, but from a user's perspective. In serverless computing, a developer simply uploads and registers their code to the cloud in the form of a function or a container. A user can invoke a function execution with a request, and the owner of the function only pays for its execution time, known as the pay-as-you-go pricing policy. Also, user can concurrently invoke multiple function executions, all handled by the scalability of the cloud. So typically, as we have seen in previous talks, serverless was used for video encoding, model training, and in general, massively parallelized data processing that focused on burstiness or cost savings. Instead, today I'm going to talk about a new workload that was not often considered. So in this work, we focus on the use case where a local 3D printer is controlled by a serverless service. The developer would upload the controller algorithm to the cloud. So when invoked by a 3D printer with the printing parameters, it starts execution and sends controlling signals back to the printers on the fly. While doing this, we need to ensure that the controlling signals are delivered timely to the local device. Although in case of network interruption, the printer can still run locally, but at a much lower quality. But why moving this control logic to the cloud in the first place? To understand that, let's first look at the printing process and why control matters. So now let's look at the specific kind of 3D printing that our work focuses on. It's called powder bed fusion, or PBF, which builds metal parts layer by layer. Each layer begins with spreading a thin layer of metal powder across a platform, as shown in the GIF, and then selectively melting the powder with a laser to form the cross-section. And this is repeated until the entire three-dimensional part is built and then cleaned and taken out of the printer. So as we see, the laser scanning is a delicate process. For example, imagine a metal sheet dividing into hundreds of cells. A simple row-by-row scanning pattern from bottom to the top causes recently scanned cells to heat up much more than others, leading to uneven temperature distribution and ultimately heat-induced deformation in the final part. So in mechanical engineering, there are already advanced optimization algorithms that target this issue. For example, SmartScan is a physics-based optimization algorithm that generates better scanning sequences for PBF. As is shown here, the optimized ordering is seemingly random, but in each step maximize the temperature uniformity. So this significantly reduced deformation compared to the picture in the last slide. So now some of you might be wondering, why do I need to hear so much about metal powder 3D printing optimization and control, since we're not in a mechanical engineering conference, right? Well, because running this algorithm in the printer itself is infeasible because of stringent time constraint and the lack of computing power. And we'll see in the next slide how this becomes an issue. So in each layer of the printing jobs, remember there are multiple layers. We saw metal powder spread across the platform, which typically takes about 15 seconds. And after that, an initial temperature map is captured by an infrared camera and quickly sent to the computer for optimization. So each optimized cell index is decided and sent to the printer on the fly with a time constraint of tens of milliseconds, very strict, depending on how long it takes for the laser to scan a previous cell. So any delay would make the prediction obsolete and hurts the printing quality. So this is repeated for each cell in the layer until the print finishes. So due to the algorithm's demand for computing power and the need to scale up and down for different printing job sizes, we would automatically turn to cloud resources. Now we will see why a regular virtual machine is less desirable here and why serverless would be a better fit. So during the printing process, only part of the time involves computation. The other part could be spreading powder or other mechanical movements. For a virtual machine, it's infeasible to spin up and terminate the VMs within seconds of this idle time. But VMs charge for total uptime, even during these idle time periods between layers. On the contrary, serverless only charges the user during execution. And the algorithm we consider also has a very large memory demand. While each index needs to be determining tens of milliseconds, it involves matrix operations over gigabytes data or hundreds of gigabytes of data, which are pre-computed for different cells. So for VMs, the memory size would be the limiting factor, dominating the cost, because all data need to be active in memory for it to be available in time. In serverless, after an initialization or a previous execution, the memory would persist for a short period of time. If the same function is invoked again, the warmed up instance would have immediate access to that data in memory. So this warm start mechanism is available in serverless products across all cloud platforms as a core feature that enables a lot of applications. And here it definitely benefits us this time. Now that we see why serverless is a good fit for this 3D printing workload, let me tell you why it is hard for it to actually work. So first, invoking function on demand can be slow for this purpose. When we invoke a function, a request is sent to the serverless front-end service. Between when the request is received and when the function workers start to run, there's a delay of over 10 milliseconds at the median, which we call the invocation delay. This overhead consumes a big chunk of our per window time budget and can break time constraints. So suppose we want to avoid this recurring invocation for each cell. We could start a bunch of workers, function workers up front and keep them running without return, basically using them just as using VMs, so that in each window, the coordinator distributes the workload across all of them and then collects the results. But when the parallelism grows, coordination overhead grows too. So sending and receiving all this data takes time. This overhead can also violate timing constraint and increase cost. So now we have seen the challenges. We are going to present how Cosmic is designed to overcome them with 3 major steps. Let me go into details for you. So first, we partition, Cosmic partitions computing and resources into groups. Suppose we have 4 function workers and 4 cells, each with data and computation that can be distributed. So there are multiple ways to arrange them. So on one extreme, we could divide the workers into 4 groups. Each group has 1 worker, and have each worker handle the entire computation for 1 cell. So when the first cell is being computed, only 1 group is active while others remain idle. Now the coordinator just need to talk to one worker at a time, but when we move on to whatever next cell being selected by the smart scan algorithm, since the workers are not active, invocation delay will be incurred. On the other extreme, we have only one group and distribute computation to all workers. At this time, all 4 workers are active during execution, so the coordinator would need to talk to each of them. When moving on to next other cells, because the workers are already running, there's no need for invocation. Well, the middle ground is that we have 2 groups and divide the workload across 2 workers, each loading 2 cells. In this case, less coordination is needed. When we move on to whatever next cell, if it's in the same group, no invocation, but the other 2 still need to be invoked. As we observe here, there's a trade-off between more coordination delay and more invocation delay in terms of how we divide the computational resources into groups. So now let's see how Cosmic would actually run. Suppose cell 1, the first cell, is selected and it was assigned to group B. Since there's no active worker, the first window would incur an invocation delay. Now cell 2 is selected and it's in the same group B again. This time we can reuse active workers for worker group B and avoid the invocation delay. Next, cell 3, following another group A, still we need to invoke the workers for them to run. But now if somehow we are able to predict that next cell falls in another group, we could preemptively invoke those workers as part of Cosmic speculation mechanism. So that when the prediction is correct and that function is needed, this time the invocation delay is hidden. So using groups and speculations, we have enabled more trade-offs and more configurations. Now we need to find the best strategy, determine how many workers we need and how many groups we should divide all the computation and data into. So to do that, we need to estimate the cost and runtime for every combination of parameters. We develop a model that takes as input the characteristics of the printing job and the measurements of serverless platform and configurations to be evaluated. With all that, we can enumerate the configurations and pick the best one. So to set up an evaluation, we set up a local desktop that runs 3D printer controlling software, mimicking the laser movement temperature as if a real printer is running. We evaluated 30 mimicked printing jobs of different shapes and sizes. So the local desktop talks to a VM in the nearest data center, and as the coordinator, the VM sends requests and relays signals from service workers back to the computer. So as to the evaluation results, Cosmic's execution of smart scan meets timing in all 30 printing jobs at a specific printing speed. So cost-wise, it outperforms all baselines in 26 of the 30 jobs. This graph takes as example a 16 square centimeter connecting rod shape printing job. Its axis shows Cosmic, 3 baseline server solutions, invoke on demand, all persistent and all active, as well as the VM-based solution. And the y-axis shows their higher cost compared to Cosmic. In particular, let me show how Cosmic reduces cost compared to VMs. This graph shows the distribution of how many times VM are more expensive than Cosmic across all 30 printing jobs in evaluation. The x-axis represents a ratio ranging from below 1, where VM is cheaper, to over 6, where Cosmic saves much more. So the median cost saving is 2.8 times. So to conclude, we explored a new serverless workload, cloud-based 3D printer control with strict time constraints. We identified millisecond scale platform delay that hindered timely execution. Our solution, Cosmic, uses function grouping and timely speculation to ensure timely execution across 30 printing jobs and reduces cost by 2.8 times at the median relative to the VM-based approach. That's the end of my talk. Thank you for listening. I'm ready for any questions.